yeah, thanks for the invitation. It's really wonderful to be speaking to you all here today. I should point out that, yeah, I'm a scientist here at the SKA, so I'm part of the science team, and it's a collective effort within the team to run the science data challenges. Yeah, and it's a really exciting project to be a part of. So today I'll give you a quick overview of our Science Data Challenge programme. I will focus mainly on the data challenge that's most recently finished, which was based on neutral hydrogen. But I'll cover the data challenges in general as well, just to give you an overview. Okay, so before I talk about the challenges themselves, I like to go back when I give these talks and talk about the actual journey of SKO data. So I'm sure you'll be familiar now with the data model of the SKA after the talks this week. But I just wanted to recap, really just to think about exactly how much data is coming through, well, will be coming through the observatory when it's online. So as you know, we'll have two sites of telescopes. We have the SKA Low in Australia and SKA Mid in South Africa. And we're going to see huge rates of data coming through as the light is collected. So all the telescopes picking up signals, sending those signals through to be correlated, correlated signals being turned into images, so converting raw visibilities into images, as we are familiar with doing when we work on radio data. But what will be different about the SKA model of data is that rather than scientists and observers dealing with those raw visibilities, instead, the observers will be given science-ready data products usually in the form of images. So quite a different model of data provision. And also you can see that through that data journey, we reduce the data down and down, but even when we end up with our images, we're still going to be, as the scientific community, will still be faced with very large amounts of data to work with in order to extract the wonderful science of the future. So the SKA observatory will be providing very large amounts of data in quite a new model of data provision. And I also wanted to recap on some of the other characteristics of the SKA telescopes. So as I just mentioned, unlike other radio observatories, SKA data will provide scientists data in the image plane rather than visibilities. The reason why SKA images will be so rich and so useful for scientists, one of the reasons is that the so-called dirty beam, which is the PSF, will be very benign. So it'll be very, very low side lobes. So you'll have fewer convolution artifacts, very long exposures, of course, and very deep images as well towards the confusion limit, which will lead us to images with a very large number of sources in them to detect and classify. So you'll get many overlapping sources. So quite new things to deal with, I would say. So that's where the science data challenges come in. So we're going to be seeing these very rich, very large data sets. And what we want to do at the SKO is we want to help prepare our community for these data sets. So we came up, the science team came up with the idea of running science data challenges with the primary goals to familiarize our scientific community, so that's you guys, with the size and the complexity of future SKA data. We want to help to support the design of future SKA observations, so to support what kind of observations you might like to propose in the future. And we want to help to drive forward the development of data analysis techniques. So there are so many data analysis techniques out there continually being developed. And we want to help you to be able to apply those to the future SKA data. As we've run the challenges, we've found that there are additional benefits to doing the challenges. So we've worked out ways that we can begin to familiarise you as the community with our data access models. We are able to do some prototyping for the future SKA regional centres. So the regional centres are where you will access future SKA data. And we also are using the challenges to encourage best practices for open science and reproducibility. So touching slightly on Shari's talk just now, we believe that open science and reproducible science is really at the heart of SKA values. So that is being able to share, say, analysis techniques easily, being able to see what other people have done to get their science. We think that's really a really good practice. And to support all of these goals, we make the data products that are produced for each challenge, we make those available publicly for the long term. So as I say, I'll just run through the first Science Data Challenge. I'll just give you a quick summary of this one. So the first data challenge was based on continuum science with the SKO, so the telescopes observing in continuum mode. And I should highlight our science working group, our extragalactic continuum science working group. So please.
We can't hear you. For some reason, we can't hear you. Philippa, we can't hear you. Lost. No, there's we can't hear you for some reason.
Can you hear me now?
Yes, yes, yes.
Okay, maybe, yes, I've just seen that my connection's unstable, so apologies for that. I'll keep going, but please do let me know again if I break up.
Okay.
So yeah, I would like to encourage everyone to come and have a look at our science working groups. If you're not involved already, you can have a look on our website and see where your science interests are represented. So our first data challenge was based on the MID telescope. So that's mid radio frequencies. It was based on mid telescope data. And it involved simulated images of continuum emission. The images that we simulated were populated by star-forming galaxies and AGN, and they represented 3 telescope integrations going to the really deep 1,000-hour integration. So as I mentioned earlier, that gives you really highly crowded images with lots of overlapping sources. So if you could increase on the right there, if you could look at that deepest image with a high, using an image viewer like DS9, you would see that there are loads of images overlapping in there. So the challenge was to find and characterize sources within those images. And you can read all about this. Our website for the first challenge is still live. You can go and have a look at that and download the data from that challenge and find out how people did. So the simulation, the image simulations themselves, they were produced by beginning with a simulated catalogue. So this was produced by Anna Bonaldi, who is one of our project scientists. And the catalogue is the T-REX, which is the Tiered Radio Extragalactic Continuum Simulation. And what this simulation does, it goes down to quite deep levels with a good agreement with observed source counts. It includes polarization and it includes realistic clustering of objects. So we take that catalogue, and for each object in the catalogue, we produce a source morphology. I will just check, can you still hear me okay?
Yes, it's all right.
Oh, that's fantastic, thank you. So for star-forming galaxies, we model a Circic profile, exponential Circic profile. For flat spectrum AGN, we model Gaussians and points. But for our steep spectrum sources, we take actual real images from the DRAGONS database, and we use those to create postage stamps to put in the images. We then simulate the telescope observing part by simulating the dirty beam. We simulate imperfect deconvolution signatures and we add noise. So please have a look at our paper that was written about the results from the first data challenge. And so I'll just go through some of the main findings from that challenge. I think my favourite finding is that of complementarity of methods. So we found that there was a tendency for teams to score well on either one or another part of the challenge. So either on finding galaxies or on measuring them. So we see that gives us the real idea that there's no single method that can address everything. And in fact, it's the collection of methods that gets the best results. Please excuse me. So yes, on to the second science data challenge. This is based on observations of neutral hydrogen. So I've highlighted the H1 Galaxy Science working group there. And some of their objectives in the future with H1 observations are to study the formation and evolution of galaxies by mapping the 21 centimetre spectral line of neutral atomic hydrogen in emission and absorption over cosmic time. And by doing that, they will be able to look at the structure and gas of cold gas in and around and between galaxies. So this second science data challenge was also based on mid-telescope observations, and it involves simulations, again, which were produced in a way quite similar to the first science data challenge. So specifically, these simulations were a 21 spectral line image cube representing redshifts from 0.25 to 0.5. That image cube was populated by the H1 content of galaxies, and it covered a 20 square degree field of view over a 2,000-hour integration time. And again, the challenge was to find and characterize the H1 sources in that cube. And this time, because it was a cube, it was quite a large data volume. So it was a 1 terabyte data cube. And again, you can read all about SDC2 on the website, which will remain live. It'll tell you, it will point you to where you can find the simulations, so you can have a look at the simulated data sets, and it will tell you more about the challenge. So I'll just run through how we did those simulations. So again, we took simulated catalogues, again from T-REX. This time we used the continuum catalogue along with an H1 catalogue that was produced for this challenge. So the H1 catalogue was created by drawing H1 masses from the alfalfa survey H1 mass function, H1 masses for the continuum catalogue were predicted. And what we needed to do was take those two catalogues and match them up. So we did that. So each source would have a continuum flux density and an integrated flux density of the H1 emission. And we applied large-scale structure to the catalogues by using the results of the P Millennium simulation, which contains clustering. And the cross-matching between those two catalogues was done according to their H1 mass. So you can read more about how the simulations were made on our website and on our paper that's coming out soon. Again, we needed to add some morphology to those sources, and to do that in SDC2, we used an atlas of real H1 sources from the Halo Gas and the Things survey. So you can see on this slide the beautiful examples, or the beautiful real observations of H1 galaxies from these surveys. So we took that real data and we modified it and added it as postage stamps to represent each source in our simulation. We then simulated the telescope effects. So before doing that, we needed to add H1 absorption signatures calculated using an absorption and emission cube. We needed to add some imperfect continuum subtraction to make the simulation more realistic. And also we needed to add some residual deconvolution signatures, again, to make the cube more realistic. And we added noise, and we also simulated some RFI flagging. So before I talk about the findings of that challenge, I wanted also to mention another aspect of the challenge, which was our reproducibility awards. So we wanted to, we really wanted to promote reproducibility because we believe that it leads to better and more efficient science. Reusability as well. We wanted to encourage reusability so that analysis methods generated by one team would be able to be used by other teams of the future. So really helping to create software that can be adapted by others, and so that previous work can be built upon for the future. So as a key feature of open science. The SKA is committed to delivering on the FAIR principles for scientific data management. So that's findable, accessible, as Shari mentioned earlier, interoperable and reusable data. So what we did was we awarded teams with a reproducibility award based on a set of predefined criteria, which you can find on our website. And we developed those criteria with the help of the Software Sustainability Institute, which is based in the UK. So what we wanted to encourage, what we looked for is the software well documented? Is it easy to install and is it easy to use? Does it have an open license? Is it findable? Does it have a repository somewhere? Does it use coding standards? And does it have built-in tests? And we had 3 levels of award, recognizing that it takes a lot of time sometimes to make your methods fully reproducible. So we had 3 levels: gold, bronze, silver, and gold. And we're happy to report that half of our teams submitted their methods for reproducibility awards and achieved the awards, which was really nice to see. So the final results from the SDC2 have been prepared as a manuscript, and that manuscript is currently under review at the monthly notices of the Royal Astronomical Society. So we hope that will be able to be published very soon. I'm just working on the comments from our reviewer. Yeah, so I think one of the most wonderful things about SDC2 was the participation from across the globe. So we had, in the end, we had over 100 people who completed the challenge, and they were made up into 12 teams from over 50 institutions. So for me, I just think it was so wonderful to see the participation from all across the world. The high-level findings from the challenge were, again, like in SDC 1, we found the complementarity of methods. So maybe unsurprisingly, different methods performing well in different parts of the challenge, but again, suggesting that in the future, it's going to be a combination of methods rather than one single method that can do everything. We found that there was a mix of new and existing techniques that were applied to the challenge, machine learning and non-machine learning. The Sophia package, if you're familiar with that, was very popular and did very well, thanks to not only how it's written, but also how well it's documented and easy to use. We did some analysis of biases and H1 mass recovery. So you can hopefully read all about that very soon. I should highlight that what we want to do in the challenges is we're not intending to perform a robust cross comparison of existing methods, because to do that, we would need to really restrict, we would have to place strong constraints on the teams. We'd have to make sure teams did things in exactly the same way, and we feel that would be very limiting. Rather, instead, what we want to do is encourage teams at all levels of expertise, so people new to the science and also people with lots of expertise. So we want to get that real inclusion of different disciplines and different levels of expertise. So I get just this map produced by our communications team really highlights the wonderful participation across the globe. So that was the second Science Data Challenge. I do also want to mention we're just about to move into our third Science Data Challenge, and this will be based on the epoch of reionization. So there is, again, a science working group you can look at if this is one of your science interests. Please do come and join. The challenge itself, the registration is closed for the challenge now. This challenge is based on the low telescope data. So as I say, the challenge has closed, but there are two parts to this challenge. The first one is based on removing foregrounds from images and visibilities of the EOR. So this is a foreground removal exercise largely, and you can have a look at the details of that on our current SDC3 website, where we will also be providing our simulated data set. We will be providing access to our simulated data sets. So have a look out for those if that's your science interest and you want to have a look. But as I say, this challenge is composed of two parts. And once the first part is finished, we'll be moving on to the inference part. So rather than providing participants with images or visibilities, the inference challenge will provide participants with power spectra with which they will be invited to infer cosmological parameters. So if that's your interest, please do look out for SDC3B, which will be starting hopefully at the end of this year or maybe early next year. So the first part, the part of the challenge that's currently running, as I say, based on foregrounds. So what we have again simulated the data for this challenge based on background EOR signal, galactic foregrounds, extragalactic foregrounds. And the next data challenge will be based, the next part of this data challenge will be based on the power spectra and inferring cosmological parameters from it. So yeah, please, I do invite you to come and have a look at our website if you're interested in following this challenge or taking part in the second part of it. So before I finish, I also wanted to talk about another really exciting aspect of the Science Data Challenges, which is working with international computational facility partners. So as we've seen, the SKA observations of the future, but also the data challenges that we are preparing at the moment will involve large amounts of data. So even the data challenges simulations that we've been preparing are quite large, involving terabytes of data. In SDC2, so in the second Science Data Challenge, we saw a 1 terabyte simulation data set. In the current data challenge, we are producing data sets that are about 7 terabytes in size. And in order to be able to provide these, we want to make sure our data challenges are as inclusive as possible and as are accessible as possible. So to be able to provide these data sets to our participants, we are working with the very generous help of our international HPC partners. So on the map here, you can see the partners who worked with us in the second Science Data Challenge. And these partners use their facilities to host our data sets, but also to provide computational provision for our teams. So teams would access the data at those data centers and would complete their analysis methods on the data centers as well. So not only does this allow us to provide realistically large data sets, but it also allows us to test some of the aspects of that future SKA regional centre model. So we can, for instance, test the access access by the community to the data. We can test technologies for having such a distributed platform. And again, we can encourage the best practice for open science. So just to have a look at some of the prototyping ideas for the SKA regional centres that we are supporting through the Science Data Challenges. The second Science Data Challenge made use of web technologies, which allowed participants to score their challenges remotely and get immediate feedback on how well they were doing. The third Science Data Challenge is going to be some of the regional centre developing teams are looking at, for example, Ruscio, which is, as I understand, it's a kind of data lake solution for storing data. The challenges will also potentially allow us to test the use of Jupyter Hub for using and deploying containers at remote centres, and also allow us to test things like Carter, which is, if you're familiar with it, it's an image viewer which is very useful for looking at both continuum and spectral line images. So before I finish, I'll just mention that our programme is continuing. We're currently working with Takuya Akahori from Japan, who is preparing a cosmic magnetism science data challenge. We are also working with the transient science working group to deliver a transient science data challenge. And really, we'd love to hear from you and what you would like to see in the future. We will be continuing producing science data challenges as we prepare for the SKA to become online. So please do keep in contact. Let us know if you have any ideas, and stay tuned for news and updates. So just as a summary, it's a really exciting part of the project to be involved with, preparing science data challenges to help prepare the community for the complexity of SKA data. we've completed 2 challenges so far, and my personal highlights of both are seeing that collaboration and method complementarity of being really strong. So we've seen collaboration between people across distributed geographically, but also collaboration between people with different disciplines, which is really exciting to see. So we've got computer scientists working with astrophysicists. So I think that's really producing great results. We've had generous support, very generous support from the international computing facilities, which has allowed us to provide realistically large data sets and to test aspects of the future SKA regional centre model. The EOR challenge, that the registration of the first part of that challenge is closed, and that will be beginning soon, but please do look out for the next part and stay tuned. Thank you very much again for having me today. Thank you.
Long live India and France friendship.